Envision where the limits of reality obscure, where the actual texture of the universe is extended and the mysterious becomes realized. This isn't a sci-fi world. It's a reality made profound, underground, beneath the boundary between France and Switzerland. Here lies the biggest machine ever created by humanity, the Large Hadron Collider. It is not only a wonder of engineering but also a testament to our mission to comprehend the universe at its most fundamental level. Yet, could this device, designed to unlock the secrets of particle physics, also be the key to opening gateways to other dimensions? The possibility of spatial gateways may evoke images of science fiction contraptions and interstellar travel. Still, here at the European Organization for Nuclear Research, also known as CERN, they represent the doorway to revolutionary discoveries. Here, the concepts of space, time, and reality are intertwined thanks to the high-speed collisions of subatomic particles. This isn't simply a tale about complex mechanisms and theoretical physics. It's an exploration into the heart of what drives our universe, made possible by the planet's largest and most powerful particle accelerator. As we delve deeper, we learn how these experiments not only challenge our understanding of the universe but also change it. CERN is nestled among Europe's beautiful landscapes, where the serene calm of nature meets human curiosity. The European Organization for Nuclear Research, a symbol of global collaboration, is home to scientists and engineers striving to unravel the layers of our reality. CERN was founded in 1954 to unite nations in pursuit of scientific knowledge and has since become the world's largest particle physics lab. Here, more than 10,000 minds from over 100 countries come together to push the boundaries of human knowledge. The heart of the organization's research lies deep underground in the Large Hadron Collider, or LHC. This extraordinary feat of human ingenuity spans a 17-mile circular tunnel where the most advanced scientific experiments ever conceived are conducted. As the most powerful particle accelerator on Earth, the LHC allows physicists to recreate conditions similar to those moments after the Big Bang by accelerating particles to near light speed and colliding them with one another. The LHC helps us explore the fundamental particles that are the building blocks of the universe. However, CERN's role goes beyond particle physics. As a hub of global scientific research, it is also a hotbed of technological advances. Innovations developed here, like the World Wide Web, have profoundly impacted our world, illustrating how fundamental research by scientists extends beyond the laboratory to affect society as a whole. This institution is more than a laboratory. It uses the universal language of research and discovery to bring people and nations together, showing that our quest for knowledge knows no limits. When we look closer at the fundamental purpose of the Large Hadron Collider, we see that its true scientific greatness lies in its ability to test and expand several foundational theories of particle physics. This machine is as much about brute force as it is about precision and the subtle details of particle behavior at extraordinarily high energies. The standard model of particle physics, developed in the 20th century, describes the forces and particles that make up our universe. However, it is incomplete. The LHC provides a unique environment where particles collide at high enough energies to detect phenomena that can either confirm or refute this model. One key aspect of the research is the study of supersymmetry, the theory that every particle we know has a heavier superpartner. These partners, if they exist, could unlock many of the mysteries of the universe, including the nature of dark matter. The LHC also plays a critical role in investigating the validity of string theory, a branch of theoretical physics that attempts to reconcile gravity with quantum mechanics. It suggests that point particles in particle physics can be replaced by one-dimensional strings. The vibrations of these strings appear to us as different particles. The energy levels achieved in this massive laboratory allow us to potentially explore these ideas, creating new particles predicted by string theory. Yet, beyond the tangible, the LHC has entered a realm that many consider science fiction. The idea of opening a portal is a term often misunderstood due to the science fiction elements of popular culture. Scientifically speaking, a portal isn't a magical doorway to another dimension as depicted in movies or on television. Instead, it refers to the possible creation of tiny black holes during particle collisions. These phenomena, predicted by the same string theory, would be incredibly short-lived and wouldn't pose a threat to our world, despite sensationalist reports from the yellow press. While in popular culture portals may be depicted as gateways to alternate realities or times, in the realm of high-energy physics, they represent an incredible journey into the unknown. Chance to notice and study conditions and particles that can scarcely exist in the regular universe. These tests had the potential to open up new components of physics. In a real sense, by examining the particles created by these impacts, researchers can gather proof that either affirms these hypotheses or sends them back to the planning stage. With its extraordinary capacity to test these hypotheses, the LHC behaves like a giant magnifying lens, amplifying the actual texture of the universe and assisting us with grasping the essential rules that govern all that we see and all that we don't. Particle physics is continually developing, and with each investigation, a discovery pushes the limits of our understanding of the universe, from finding key particles to testing the constraints of physics. The accomplishments of this research place are great. At the forefront of such scientific advances is the discovery of the Higgs boson, a particle integral to the mechanism that gives mass to fundamental particles, found in 2012. This advancement confirmed a pivotal piece of the standard model of particle physics and won the 2013 Nobel Prize in Physics. The existence of the Higgs boson, frequently called the God particle, has answered key questions about how particles get mass. This discovery was a victory of theoretical physics, as well as of open science, as demonstrated by the new open release of the Higgs boson discovery by the CMS collaboration, which marks a significant commitment to open science. Furthermore, collaborative research and transparency foster a global scientific dialogue in which hypotheses can be thoroughly tested and new speculations can arise from shared knowledge. This release, which includes the unique consolidated software developed to search for the Higgs boson, allows scientists worldwide to explore the intricate details of this monumental discovery. The resulting probability model, with almost 700 parameters, captures the complexity of the experimental data, offering a multifaceted portrayal that challenges even the most complex perceptions. This openness not only democratizes access to cutting-edge science but also enhances the collective ability to validate and build upon key discoveries. However, the journey did not end there. CERN has played a critical role in other major discoveries, such as the separation of antimatter and the detailed study of quark-gluon plasma, a state of matter believed to have existed shortly after the Big Bang. Another experiment called ALPHA has successfully captured antihydrogen particles, opening a new way to study the properties of antimatter. This pioneering work aims to address the question of why the universe is composed mainly of matter, despite the Big Bang theory suggesting there was an equal amount of matter and antimatter. Another cornerstone of CERN's research is the study of quark-gluon plasmas using the LHCb experiment. By focusing on quark-gluon interactions, researchers are diving into the study of the strong force, a fundamental force that holds atomic nuclei together. Every discovery at CERN not only adds a new layer to our understanding of particle physics but also pushes the limits of technological achievement. Under such extreme conditions, these experiments require the precise coordination of many scientists and state-of-the-art technology, reflecting the astonishing collaboration of people around the world. As you might have realized by now, the LHC isn't just an innovation circle, it's a finely tuned experimental environment in which the most fundamental questions of physics are addressed. So, how does the Large Hadron Collider work? The process begins by feeding light beams into the collider from a chain of small gas petals. Every proton starts its journey in a simple bottle of hydrogen, where electrons are taken from it, leaving bare protons ready for acceleration. These protons go through a series of gas petals, gaining energy at each stage, until they finally arrive at the LHC. Once in the collider, the proton beams are boosted to extreme energy levels, reaching 6.8 tera-electron-volts, TeV, by the latest 2024 updates. This extraordinary energy is essential for the protons to collide with enough power to break into a range of subatomic particles, some of which might have never been observed before. The entire process occurs on a scale that is hard to fathom with ordinary interactions, but we'll still try to explain the concept. 1 tera-electron-volt is roughly equivalent to the kinetic energy of a flying mosquito. Therefore, 6.8 TeV is about the total energy of around 6.8 flying mosquitoes. However, that energy is packed into a particle that is incomprehensibly smaller than a mosquito. A proton is a subatomic particle, meaning it's part of the core of an atom and has a diameter of around 1 femtometer, fm. In comparison, a mosquito is about a quarter-inch in length. To visualize this difference, if a proton were the size of a pea, a mosquito would be the size of a huge skyscraper. Yet all the energy of a moving skyscraper would be packed into such a tiny object. So, let's continue. Of critical importance in the entire process is the achievement of proton beam stability, a state when the beams are dense and well-centered. The beams are carefully controlled or compressed to ensure they crash at the detector where they can be most effectively studied. This process involves precise control of the many magnets around the LHC ring that guide and focus the beams. The collider has already produced its first stable beams at rare energy levels in 2024, marking the official start of this year's physics data collection season. The third year of LHC Run 3 promises 6 months of proton collisions with energies of 13.6 tera-electron-volts at much higher levels, glows than prior to significance more. Crashes for information, social affair tests. This stage will be followed by tries, different things with lead particles, giving an alternate arrangement of conditions to study. Likewise, this year, the MapBook Insight experiment has already accomplished an achievement in particle physics by measuring the width of the W boson for the first time. This boundary, significant for understanding the weak force conveyed by the W boson, was viewed as 2,202 Uber-electron-volts, which concurs well with the predictions of the Standard Model. Besides, at the very front of examining the essential imbalances of our universe, the LHCb coordinated effort has made significant progress in grasping the complex exchange between matter and antimatter. In ongoing trials, they have examined the behavior of the neutral d meson and neutral strange b meson, revealing new layers of intricacy in how these particles abuse charge parity, CP, symmetry. The neutral d meson, consisting of a charm quark and an anti-up quark, has shown a curious quantum peculiarity. It can unconstrainedly change into its antimatter partner and back again. This peculiarity has been caught with remarkable accuracy in recent datasets from the initial 2 LHC runs. The ongoing study aims to identify potential CP violation in these changes, which might shed light on the power of matter over antimatter in our universe. Also, the neutral strange B meson, consisting of a bottom quark and an anti-strange quark, showed time-dependent CP violation while decaying into quark-gluon plasma. This observation marks a significant development, as it was achieved with statistical significance beyond the conventional discovery threshold. In particle physics, these results not only confirm the known behavior of these particles but also open new avenues of investigation. With the LHC now operating at higher luminosities, future data could further refine these measurements, potentially leading to new physics beyond the Standard Model that could explain dark matter and the matter-antimatter asymmetry in the vast universe. In the realm of data surrounding the Large Hadron Collider, LHC, numerous myths and thrilling stories have flourished. Today, we'll attempt to clear up these confusions and explore the real scientific picture. Diving deep beneath the surface, one common legend is that tests at the collider can incidentally produce black holes capable of consuming the Earth. Now, while the LHC can make minuscule black holes, they are on the quantum scale and dissipate immediately through a process known as Hawking radiation. Stephen Hawking's theoretical predictions convince us that these infinitesimal black holes pose no threat. They provide intriguing insights into gravitational forces but are far from the end-of-the-world scenarios depicted in science fiction. Another dramatic case is that the collider opens gateways to other dimensions or causes devastating natural disasters. Such situations, although popular in films and on TV, are not supported by any scientific data. The LHC's primary mission is to test the predictions of theoretical physics, to study the particles and forces at work in the universe, not to disrupt the fabric of reality as we know it. CERN works under strict safety protocols, Extensive checks and risk assessments are performed regularly to ensure that all experiments are safe, not only for researchers but also for the environment. Finally, tales of paranormal phenomena or secret experiments are entirely unwarranted. As a straightforward scientific institution, its research is published and accessible to the global academic community. The commitment to transparency extends to public documentation, open databases, and collaborative projects across continents. As we continue our journey, we need to remind ourselves to rely on proven facts and scientific research. As we delve into the theoretical underpinnings of multifaceted research at CERN, we are exploring ideas that push the limits of our understanding of the universe. These areas of physics consider the possibility that our universe may not be limited to the 3 dimensions of space and one of time that we experience daily. The possibility of higher dimensions comes from theories such as string theory and superstring theory, which both suggest that particles are not zero-dimensional points but rather one-dimensional strings vibrating in multidimensional space. These theories propose the existence of up to 10 or 11 dimensions, which might help resolve discrepancies between quantum mechanics and general relativity. In practice, researchers at CERN use the Hadron Collider to examine these higher dimensions indirectly. One approach is to look for signs of particles that might exist only in these higher dimensions or effects, such as the creation of minuscule black holes. The search for extra dimensions is not just a quest for knowledge about the fabric of space. It also has practical implications for understanding the fundamental forces of nature, including gravity. If extra dimensions do exist, they might explain why gravity is much weaker than the other fundamental forces. Beyond theoretical interest, the study of higher dimensions could lead to technological advances in fields such as quantum computing and materials science, as these ideas drive the development of new technologies to detect and measure tiny and fleeting phenomena. As we journey deeper into the unknown frontiers of particle physics, another CERN initiative, the Search for Mysterious Particles Project, SHIP, is set to transform our understanding of the universe. The ambitious project aims to detect elusive ghost particles that might hint at higher dimensions beyond our 3-dimensional space. The SHIP experiment relies on an innovative concept. Unlike conventional collisions at the LHC, where particles smash into each other, SHIP will direct them toward a specific target, increasing the likelihood of detection. The method is expected to be up to 100 times more sensitive than any current equipment at CERN. These ghost particles, possibly composed of dark matter or other unknown components of dark energy, remain invisible under normal circumstances due to their very weak interactions with ordinary matter. The implications of discovering such particles are profound and will likely alter our core theories of physics. Alongside SHIP, plans are underway for a future round collider, which should be a leap forward in particle collision technology. This collider is expected to reach its full potential by the middle of the 21st century and will push the boundaries of human technology and scientific research. Potential discoveries made at SHIP and the Future Round Collider could open new chapters in the history of our universe, from advancing our understanding of fundamental particles to creating new technologies. The implications for particle physics are immense, offering a glimpse into the very fabric of the universe and perhaps even into the higher dimensions that weave it together. As CERN continues to support its scientific accomplishments, the quest for knowledge moves forward, promising a future where the mysteries of the universe will be uncovered, one collision at a time.